We've learned to solve exponential equations by writing both sides of the equation with a common base. I'm now going to show you how to solve these three exponential equations where it's impossible to find a common base. We're going to start with this one here. So I have two random numbers, 3.14, and that's equal to 2.72 to the exponent x. And we're going to solve this. Now, if you try and write both of these numbers as powers with the same base, you're not going to find a whole number answer for that clearly. So we need another method. You could guess and check the solution, but that'll take a long time and you're going to have limited accuracy. So the method we're going to use here is using a function called the logarithm, which we'll pronounce log. So the log function, it's defined here implicitly. The log of y is equal to x if 10 to the exponent x is equal to y. There's no explicit way of stating it. It's defined implicitly in that way. So it allows us to rearrange an exponential equation. Because of the way it's defined, it has these three very useful properties. The log of the product of two numbers, that is the log of what you get when you multiply two factors, is equal to the log of the first factor plus the log of the second. The log of a quotient, that is the log of a fraction, is equal to the log of the numerator minus the log of the denominator. And finally, the most useful rule, the log of a power is equal to the exponent times the log of that base. We're going to use this key rule here to turn our exponential equations into simple linear equations. So back to our problem. To solve this, I'm going to take the log of both sides. So the log of the left is the log of 3.14. The log of the right is the log of 2.72 to the exponent x. Now the meaning of the log of 3.14 is find the exponent you must raise 10 to for the power to be equal to 3.14. And your calculator is equipped with a log button to run that function for you. So 3.14, we take its log, and it gives us 0.4969. Now over on the right, we have the log of 2.72 to the exponent x. We're going to use this key rule right here. The log of a power is equal to the exponent in the power times the log of the base. Here, the power is 2.72 to the x. The exponent is x, the base is 2.72. So using that rule, this is equal to the exponent multiplied by the log of just the base. Now the log of 2.72 is 0.4346. So that makes x equal to 0.4969 over 0.4346. Which is 1.14. Now we can verify that that's correct. If you raise 2.72 to the exponent 1.14, it comes out to 3.14, to within rounding. Obviously, the more decimals we carry with us as we perform this, the more accurate the answer is going to be. Okay, let's have a look at our second question now. So here we have 7 times 5 to the x is equal to 3 times 2 to the x plus 1. So we can employ the log rules again, but it's just going to be a little bit messier because we have more things to deal with. So the first thing I'm going to do is take the log of both sides. So we have the log of 7 times 5 to the x, and that's equal to the log of 3 times 2 to the x plus 1. I'm going to put brackets around here to make it clear that we're taking the log of the entire left and the entire right. First rule I'm going to use is this one here to split up the products. So the log of a product is equal to the sum of the logs of the individual factors. So on the left, that's going to turn into the log of 7 plus the log of 5 to the x. On the right, that's the log of 3 plus the log of 2 to the x plus 1. I'm now going to simplify things even further by employing this rule here. The log of a power is equal to the exponent times the log of the base. I'm going to use that here and here, so I have nothing but addition and multiplication in my equation. I've gotten rid of my exponents, making it much simpler. So we have the log of 7 plus x times the log of 5 is equal to the log of 3 plus x plus 1 times the log of 2. I'm now going to bring all of my variables to the left and all of my numbers to the right. Now when you see the log of 7, what I want you to understand is that's not a variable. You can consider that a known number. You just simply take the log of 7 and you have this decimal here. To get a bit more accuracy in our answer, I'm just going to keep writing it as the log of 7 and plug everything in at the very end. So on the left, we have x log 5 minus x plus 1 log 2. And on the right, we have the log of 3 minus the log of 7. Okay, everything's accounted for. I've just moved all the variables to the left by subtracting, and all of the known numbers to the right also by subtracting. So on the left we have x times the log of 5 minus x times the log of 2 minus the log of 2. That's equal to the log of 3 minus the log of 7. So on the left we have x times the log of 5 minus the log of 2. And on the right we have the log of 3 plus the log of 2 minus the log of 7. That means that x is equal to the log of 3 plus the log of 2 minus the log of 7, all divided by the log of 5 minus the log of 2. So at this point, all you need to do is very slowly and carefully enter that into your calculator. I suggest using brackets for the numerator and brackets for the denominator to make sure things come out right. So I've got to open a bracket, take the log of 3, add the log of 2, subtract the log of 7, close my bracket, and divide by, I'm going to open up a bracket again, the log of 5 minus the log of 2. So our solution is negative 0.1682. Now at this point, we can verify that that solution is correct by plugging it in. So if our solution is negative 0.1682, on the left we have 7 times 5 to the exponent decimal 1682, and that exponent's a negative. So on the left we have 5.3398. On the right we have 3 times 2 to the exponent 1 minus decimal 1682. Giving us again 5.3397. So that verifies that our answer is correct, because when plugged into the left and the right, it gives the same result.